So um, this is a bit of more exploration, sort of freestyle exploration. We did that with 1 qubit, and now we're gonna do this with 2 qubits because I think that's where things start getting interesting in terms of 1 qubit is just 1 qubit. So if we just restrict to 1 qubit, then you can play with how much information you can encode in there. And maybe I'm gonna do a video on that. So how do you encode how much information can you get into 1 qubit? But when you have 2 qubits, then you have entanglement, or you can actually program entanglement. Not only that, you can play with partial measurements, which then kind of uh, will help you eliminate potential states. So that's one of the things that some of the algorithms that we've gone through do actually, and I think that's playing with correlations is what's pretty beautiful actually, and the most basic type of correlation, it's just it's because of conditionality. So that's the way you program it, right? So basically you say if 1 qubit is 1, so if qubit 0 is 1, then perform an operation on qubit 1, right? So you're now kind of connecting both qubits. So a simple example, this one. So if qubit 0 is 1, perform an X operation on qubit 1. You can also have a control Y, so just do a Y operation, right? And then you have fancier stuff like a control rotation, right? So it's like if one perform a control rotation on the Z, control Z rotation on a given like angle, pi, like for example pi, yeah, divided by 2 or by 3, whatever. Now the beauty of this is that what is that? That's just like if, right? So if you is a conditional. So if you do that, then do that. The trick here is that when we put the control qubit into a state where it is not certain of the answer, so it's in a superposition. It doesn't have to be a perfect superposition like 50-50, but it can be, let's say we're going to rotate that um, say just like a little bit, right? And so now those qubits become entangled because whenever we measure one of them, then we're going to know how the whole system behaves. But before we do that, we're not. So and by doing that, what we can basically play with is we can play with entanglement in a way that we build a correlation and then we play with it so that potential solutions or potential final measurements are more probable or not, or they're just out of the picture completely. In this case, what I find interesting is that the state vector is this way. So it means like it means that 1 0 and 1 1 are completely not possible. That's interesting. Well, yeah, of course, because a rotation on the z-axis on something that's 0 is always going to be stay 0. So the interesting thing here would be, what if that is in this state, right? And then now we've rotated that qubit as well. So a z rotation would have an impact. That's interesting. That's interesting. That's interesting. So and that's how you kind of that's how you entangle things, right? Because you make things depend on each other, and by that you build a correlation. What I want to explore is how can this be used and how can this be exploited to solve problems. What we've seen so far is that in some instances, the when you if you combine certainty, if you combine entanglement with the creation of superpositions, um, some of the possible states get destroyed, and then so you can kind of you can then build circuits that build circuits that map that actually help you solve certain types of problems. But I haven't seen an algorithm yet that it's clearly an algorithm, right? um, I have seen so far only hard-coded functions. So it's like you just hard code something and then you call that, hey, that's my algorithm. I know of Shor's algorithm. I think it's going to be a bit more complex to break down, because I think it's a heavy algorithm to understand. But that's maybe the one that seems to be an actual algorithm, that's built entirely on a circuit. So let's see if we do that at some point. But that's basically how you create entanglement. Um, and you can do that among like completely different dimensions. I mean, you can get crazy. You can get crazy because you can just do that. Yeah, I mean, you can do it this way, and then before that, you can still apply a like an actual Z rotation. Wow, look, that's beautiful. So you can. That's it's cool because just look at that. That tells you how many information here we have encoded. It's not only just probabilities, but it also has this three dimensionality, right? Like this dimensionality of that state is a 1 1, but 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 it's a mixture of complex and negative, right? So, and that negativity is what you play with later on too, because if I now do something like that, ooh, that's cool. So it seems like we've now brought everything up. So now it's kind of like it's everything mixed up. Interesting. Interesting. Yeah, that's there's a lot of stuff to do in here. A lot of stuff to do. So that's one of the things that you could do with 2 qubits. And then when you add a third qubit, then it just gets even more interesting, I guess. So if you do that, that gets even like the space of the space you have to play with is even bigger, right? Because then you can entangle. Well, what's more? Let's add two more. So you've got that, and then the thing here is now you can do things like, so this is another sort of entanglement. That's interesting though, because in theory I've created a. You see, it's just not obvious. Assuming that's correct. Um, assuming that's correct, and that's the density matrix which I haven't explored yet, and I think that is something definitely worth doing, because here basically you can see, so that's the complex dimension, and this is the real dimension, and then you've got colors as in like positive or negative. So here you don't have uh the yellow thing, because you basically have positive and negative, and then you distinguish between the complex and the non-complex dimension. um that's interesting. And so you could even still do something like that, which creates even weirder correlations. Nice. So it boils down to this, right? When we're playing with entanglement. um So the negativity of some of the possible states, that's definitely something you can mathematically understand as, you're going to cancel things out. But the complex part, the complex dimension, is something that I have still to wrap my mind around. um how what is that beneficial for, and how can you use that? Cool. Interesting. Really interesting.